Now that we have reviewed the mathematical background related to asymptotic algorithm analysis, now let's start discussing how we can define the complexity of specific algorithms. So we have some good news and bad news. By now, you know how to do object-oriented programming. But the bad news is you need to learn now good programming. That means from now on, we're not interested in whether you can provide some functionality. In other words, you can write a program that solves what is requested from you. But now we request that you write your programs in a good manner. By good manner, we mean you obey to the rules of software engineering, but also your algorithms are as simple as possible. By simple, we mean the algorithms should not have very high complexity rates. So let's start some discussion on this. Consider a question like you're given a group of n numbers and you want to find the kth largest. Now, finding the largest value is simple. How about the kth largest value? Now, you can find this. There could be some solutions. The first solution could be you read these n numbers into an array, okay? Then you can sort them. You either you write your own sort method, or in fact, there are many sort methods. Also, the array class has a sort method for that. So you can sort them, and it will sort the numbers from the largest to the smallest, or in the reversed order, doesn't matter. And you will return the kth largest out of this array. That's simple because the array is already sorted. So you just go to the index k. Or another solution. Now here there's a problem, and the problem is, what if the array is too large? Like if you have, say, 1 million elements, can you store 1 million integers or floats in an array? You may have an array large enough for that, but you might need such arrays, many of them in your program, so it would be too costly to have such an array in your program, especially in the case of restricted environments, like assume you're developing this program to run on a simple sensor where you don't have enough memory. Then you might not have enough memory for an array of size 1 million integers. Another solution could be, rather than having an array of 1 million elements, well, have an array of k elements, where k is, remember, we're looking for the kth largest value. So have an array of size k, and while reading the input, keep in the array only the values that are the largest. Okay, so you have space to keep only largest k values, so you keep them. By the time you have read all of the input, you will have lost all the values after the kth largest, but you don't care about them. So just return the last element in the array, which will be the kth largest element. But now, this solution is still not very good, although it's better than the first one. It's not sufficiently good because it's possible that k itself could be as large as, say, 500,000. So still, it would be quite difficult for you to store such a value. Okay, so that means we should find methods that can keep up with this. Note that in this example, for example, we are not looking at how many instructions are being executed, but we are looking at it in terms of memory footprint. In general, when we're talking about the algorithms, people mostly talk about the worst case behavior. Well, you can look at the best case, first of all, but best case is not very important for us because in general, you will not have that best case, you will have worse behaviors. So your algorithm typically would not be working if you consider only the best case. So you should not be looking at only at the best case. Most important thing would be looking at the worst case scenario, because we want our programs to be properly functioning even in the case of worst case behavior. But you should also consider the average case behaviors, because it is possible that that worst case is very rarely happening. And if so, it depending on your problem, that could be tolerable or not. Now, in some cases, you cannot even tolerate the worst case behavior, even if it happens one in a, say, billion occurrences. Like, say, if you're flying a plane, you cannot say the plane crashes one in every million miles, because that still means once in a while your planes will crash. But in some cases, say, if you're talking about the registration system, if the system fails one in a million attempts, that might be tolerable. So we should be interested in the best case behavior, but the more important would be looking at the worst case behavior and the average case behavior. So we should be able to classify our algorithms. Now, we will be dealing in this section with how we classify algorithms according to their behavior in the asymptotic growth. We will be defining the theta, little o, and little omega functions. We will be also defining the big O and big omega functions. Big O is written in blue because it's the most frequently used one, but still we have to discuss the others. And we will be discussing some rules to manipulate the big O expressions and the typical growth rates. So, asymptotic growth is, as we said, the rate of growth of a function, especially when the size of the problem becomes very large. Now, if you try to classify functions according to their behavior in the asymptotic case, then it's obvious that there are three classes. Functions of different functions can fall into three groups. The first group would be the functions that are growing at the same rate. The others would be functions that are growing faster than the one you're looking at, say f of n, where f of n is a particular differentiable function, and the functions that are growing slower than n. So we would like to find out which functions are growing at the same rate with f of n. We will consider all those functions equivalent. They're not exactly the same, they're not equal, but we will consider them to be equivalent because as n goes to infinity, their behaviors would be similar, they will be comparable. But there will also be functions that are growing faster than f of n, which are typically worst methods, and those that are growing slower than n, so they would be better than f of n. So we first define the theta function. Consider two functions, f of n and g of n. If they have the same growth rate, then for small values of n, f of n could be better or worse than g of n. I don't care about that. What I care about is what happens as n goes to infinity. If f of n and g of n have the same growth rate, if you look at f of n over g of n and take its limit as n goes to infinity, it should converge to some constant c, which is a positive value. Note that c should be a constant value, but I don't care what the value of c is. So in other words, for example, if f of n is twice as g of n, limit of f of n over g of n would be 2 as n goes to infinity. You might say f of n is twice as bad as g of n. I don't care. For me, it's some constant value, so it's tolerable. So no matter how large or small c is, the important thing is it's a constant value. As long as it's a constant value, we will consider also such functions to be in the same rate of growth with f of n. And we will denote such functions using the theta notation, as in here saying f of n is equal to theta of g of n. Now, if f of n grows slower than g of n as n goes to infinity, then limit of f of n over g of n would be 0 because f of n is growing slower. And we will denote this with the little o here, saying f of n is equal to little o of g of n. So to repeat, the theta class shows the class of functions that are equivalent with f of n, whereas little o class shows the functions, the class of functions that are growing faster than f of n, or in other words, f of n is growing slower than all of these functions in the little o of g of n class. Little omega would just be the inverse, so f of n this time is growing faster than g of n. So if you take the limit, it should be going to infinity. So we will denote this with the little omega function. So all functions in the little omega class would be the functions that are growing slower than f of n. If g of n is equal to little o of f of n, then we can just write the inverse. F of n would be equal to little omega of g of n. So for example, if you compare two different algorithms, one has complexity relative to the function n, and the other one would have complexity n squared. So here we are assuming that f of n is equal to n and g of n is equal to n squared. Note that these are two separate functions doing the same thing, but one has complexity n, the other one has complexity n squared, like developed by two different people. If you take limit of f of n over g of n, in other words, the limit of n over n squared, that would be 0. So we can say n is equal to little o of n squared. If you just look at the inverse, then you would say n squared is equal to little omega of n. So based on these definitions, we can define a relation of equivalent, which is actually the class of functions that have the same rate of growth. So relation of equivalence gives a partitioning over the set of all differentiable functions. These functions actually correspond to the complexities of different algorithms. So we're looking at many different algorithms, different ways of doing the same thing. But when you look at all these different approaches to solve the same problem, if I can define functions with different complexities, but saying these are equivalent in complexity, then I can say these algorithms are also equivalent to each other. Or then we will also define algorithms that are worse than these and that are better than these. So functions in one and the same class are said to be equivalent with respect to their growth rates. So two algorithms have same complexity if the functions representing the number of operations, their complexities have the same rate of growth, and among all functions with the same rate of growth, you can pick anyone. Then, for example, you can look at the cost. So you can, if you can say you had 10 different solutions to the same problem, or 10 different softwares that are doing the same thing. If you can find that 5 of them are equivalent, then you can pick any one of those 5. Now at that point, since their complexities are the same, which means their performances are comparable, then for example you can pick the one that's cheapest. So compare again two functions. F of n is equal to n, and g of n is equal to n plus 1 over 2. So we take limit of n over n plus 1 over 2, which is equal to 2. I don't care if it's 2 or 3 or 1,000 or 10,000. The important thing is it's a constant value. Therefore, I decide that these two functions, these two methods, implementations, have the same rate of growth. So we can say n plus 1 over 2 is equal to theta of n. So they have same rate of growth, and it's a linear function, as you can see, since it's theta of n, it's linear. Now another example, we have this time two separate algorithms. One has complexity n squared, and the other one has n squared plus 6n. Now you could easily say that n squared plus 6n is larger than n squared. But if we look at the complexity analysis, n squared over n squared plus 6n gives us 1. It's a constant value. So we will say these are equivalent. Note that I'm not saying they're equal. We're just saying they're equivalent. So we will say these two methods have the same complexity. They have the same rate of growth in complexity, and that rate of growth this time happens to be quadratic because it's theta to the theta of n squared, whereas in the previous case it was theta of n. So there it was linear. Here it's quadratic, theta of n squared. So it's more complex. So these two methods are more complex compared to these two methods. But each group in themselves, they are equivalent. Now let's consider a method with complexity log of n and another one with complexity log of n squared. Again, when you take the limit, it's a constant value, 1 over 2. So we will say, again, they have the same rate of growth, but this time it's theta of log n, so it has logarithmic rate of growth. Let's first look at the first group, to the group of theta of n cube. So n cube, an algorithm with complexity of n cube would be in this group. Another algorithm with complexity 5n cube plus 4n would also be in this group. Even an algorithm with 10 to the 5, which means 10,000, 100,000 times n cube plus 4n squared plus 6n, even that would be equivalent to n cube, because we are looking at the term with the highest degree, which is n cube, and the factor in front, it's not important how large it is. The important thing is this factor is a constant value, so I can just discard it. So I don't care if it's 10 to the 5 or 5 or 1. These three methods, they all have complexity in the theta n cube. So these three methods are equivalent, we say, as n goes to infinity. If you look at theta of n squared, then again, n squared, 5n squared plus 4n plus 6, or n squared plus 5, they're all in the same group. Similarly, for theta of log n would be there. Log of n squared would be in that class. Log of n plus n cube, still even that one is logarithmic. So when we are comparing functions, if g of n is equal to theta of f of n, we say they have the same rate of growth. We have already discussed this. For different rates of growth, either g of n would be equal to little o of f of n, or g of n would be equal to little omega of f of n. This is already what we have discussed, so this is just a summary slide here. How about the big O notation, the famous big O? We say f of n is equal to big O of g of n if f of n grows with the same rate or slower than g of n. So mathematically it means either f of n is in theta of g of n or f of n is in little o of g of n. Well, putting aside these mathematical definitions, what big O actually means is big O always defines as an upper bound. And one thing you should note about this upper bound is when I talk about an upper bound, it doesn't necessarily mean that algorithm hits that value. I'm just saying this algorithm's complexity does not exceed this limit. It's either below or at most it is this much, not more than this. That's why we call it an upper bound. But once again, let me repeat that it doesn't necessarily say the complexity of this algorithm would be as high as this. Now you can guess that I can define the upper bound as infinity because nothing will be exceeding infinity. You're right, in mathematical terms that's correct, but we would like to find the lowest value, the closest estimation for the upper bound. So mathematically it would be correct, as I said, to say every algorithm's complexity can be limited, upper bound by infinity, but that would be a correct but useless information. We would like to find the closest estimation. For example, I might have an algorithm which in fact has complexity n plus 5. So it would be in theta of n. Therefore, I could say big O of n for this algorithm. So up to this point, to the part I have highlighted, it's fine. Now, what if your friend comes and says, well, I'm claiming that the big O for this algorithm is O(n) square. Another one says O(n) cube. Yet another one says O(n) to the 5. Now, all of your friends are actually giving correct information, but the problem is their estimations are actually very exaggerated. I would like to come up with something as close as possible, if I can define it. So in this case, big O of n would be the best response. Also note that n plus 5 is greater than n. But remember again, we're looking at the behavior as n goes to infinity. So that plus 5 is not important. That will be actually discarded in the notation. There's also the definition of big omega, which is actually just the inverse of big O. Well, remember what big O was. Big O was defining as the upper bound. So big omega, since it's the inverse, it's defining as the lower bound. Sometimes we also need that information. We're mostly interested in the upper bounds because we would like to know how bad our algorithms can go. But it would also be nice in many cases to know also what's the best we can achieve. So big O defines that. So if g of n is equal to big O of f of n, just the inverse, f of n is equal to big omega of g of n. So that means fn grows faster or with the same rate as g of n. So let's talk about some rules to manipulate the big O expressions. Let's look at first rule 1 and first part A. So if you have two algorithms with different complexities, T1 and T2, T1 of n has complexity defined by big O of some f of n, whatever it is, and T2 similarly is defined by big O of G of n. Now if you look at their sum, T1n plus T2n, that would be the larger of the two big O notations. In part B, if we have two algorithms that have T1 of n and T2 of n, and now we're multiplying T1 of n with T2 of n, then the complexity would be big O of f of n times g of n. Now, what does adding the complexities of two algorithms or multiplying the complexities of two algorithms mean? We will be seeing that in the following slides. For the moment, just let's focus on the mathematical information here. We'll be discussing the corresponding examples. If T of n, in rule 2, if T of n is a polynomial of degree k, then we can say T of n is equal to theta of n to the k. And in rule 3, log base k of n is equal to big O of n for any constant k. That is, the logarithms grow very slowly. Now let's look at some examples. If we have n squared plus n, that would be equal to big O of n squared, because we're looking at the term with the highest degree and disregarding any low order terms. If we have two algorithms, one with n and the other one with log n, their multiplication would have the complexity of big O of n times log n. And if we have n squared plus n times log n, now you should scratch your head. You're going to merge several information here. Now what we first need to remember is log of n, remember, is less than n, because logarithm grows slower than n. Okay? Then n times something less than n would be less than n squared. Now on this side I have n squared, and here I have something less than n squared. So I can discard this term which is known to be less than n squared. So the important thing for me would be n squared, therefore this has complexity O n squared. Now, if we have many algorithms with different growth rates, how do I know which one is growing faster or slower? We should know some basic typical growth rates, because the others typically could be mapped to one of these. So, if an algorithm has some constant complexity, say C, whatever that value of C is, we will write for that big O of 1, and that's the simplest one. Actually here it means it's independent of n. This is just like, assume you have a method, you have a program that's finding the value independent of the size of the input. So whatever the number of values is, it's just say returning the temperature outside. Then it's independent of the size of the input. So that would be the simplest. So even if n goes to infinity, your program always has the same complexity. And this is very rare, by the way, such examples. Another one would be logarithmic. So as n goes to infinity, it's growing slowly. Remember the logarithm function. We have log square of n, which is slightly faster. Linear, you already know. N log n, as we just discussed in the previous slide, is better than n squared, and n cube is typically worse. 2 to the n, or anything, any constant value to the n, is just exponential, and n factorial would be the worst. Note that factorial is worse than exponential. So this shows actually the growth here. This curve, this line here is 10 times n, and this is 20 times n. These are both linear. By the way, note that the scale of the x-axis and the scale of the y-axis are not the same because of these functions that are growing very fast. I had to draw it that way. That's why 10n does not appear to have a degree higher than 45. But as a factor in front of n grows, of course it's moving up, but not very significantly. If you look at n log n, this 5 here is not important. This is n log n. This is better than n square, but worse than linear, of course. Here we have n squared. The 2 here again is not important. The important thing is n squared. So n squared is growing very fast. This is the exponential. See the difference between quadratic and the exponential. Now, and you also hear that factorial is really terrible. Exponential and factorial are just going towards infinity very fast. Now, in most cases, when you're running your experiments, you will be running it with small inputs. So if x-axis shows the value of n here, you will be looking at this area and all algorithms will appear to be similar. So when you're trying to compare different software, if you're running it with small example scenarios, you will not observe any difference and you might be misled to buy the cheapest one. However, the cheap one could have a complexity of n factorial or 2 to the n or 2n cubed or n squared, whatever. That means as the size of the input grows, suddenly those software become unusable. Okay, that's why we are interested not in the small values of n, but we are interested in large values of n. And note that for the case of factorial, exponential, and even for quadratic, as the size of n grows, very fast you will realize that such software will be useless. So that's why we're saying computer engineers should understand algorithm complexity, algorithm analysis. This is a very important topic because many of the applications you will find will be in this group and they will be totally useless in a real scenario. So this is just zooming into this dashed rectangle here. If you look at that part, you will see that factorial or exponential are better. Pay attention, they are better than 10 times n, which is the linear case, for values that are small like 2, 3, 4, 5, whatever. Okay, but soon they start growing. More important thing, they grow so fast that I don't care how cheap they are. I will never buy such software because they're completely useless in a realistic scenario, as I mentioned earlier. So here we have some examples. If we compare n squared, if you have predicates like n squared is equal to big O of n squared, that's true. If we say 2n is equal to big O of n squared, that's again true because remember, big O defines as the upper bound, n squared is above 2n, so that's correct. The more correct one would be on, that's also true, as we can see here. This is a better, sorry, let me pick the pen here. So this is a better representation than this one, but still mathematically On square is also true for 2n. If we compare n with On square, it's similar. That's also true. But when you look at n square is equal to On, this is not true. Okay, because On is not an upper bound for n square. So this predicate is not true, so I should correct it as not equals. We said 2n is equal to On, we already discussed this, and n is equal to On, that's also obvious. Look at the one examples below the line. Now these are, pay attention, not for O, but for theta. So saying n square is equal to theta of n square, that's correct, definitely. Saying two n is equal to theta n square is false, while saying 2n is equal to On square was true, because in the one above, in this one, On square was an upper bound. But here we're talking about theta, the equivalence. So we cannot say 2n, which is of the class of theta n, is equal to theta n square. That is not correct. Don't forget that theta does not define upper bound. Theta defines equality. Equivalence, sorry, not equality. So this was false. Saying n is equal to theta of n squared, similarly, that's not true. Saying n squared equal to theta of n, obviously that's not true. Saying 2n is equal to theta n, remember, we don't care about these factors, constant values, so we can discard that constant value. So it would be n equals theta of n, which is true, which is also written in the last one. That was also true.